This is part 2 of a two-part introduction to electrochemical cells. Make sure you have seen part 1 before you view this video. In part 2, we'll explain what happens in the salt bridge and why it is necessary for the cell to function. We will also review what we've learned in parts 1 and 2. In order to understand what the function of the salt bridge is, we'll see what would happen if we didn't have the salt bridge. As positive ions or cations are formed at the anode and enter the solution, an excess of positive charge would build up in the zinc nitrate solution. Notice we have a total of 4 positive charges and 2 negative charges on the ions depicted in this solution. And looking at the cathode on the left, as copper cations leave the solution and attach to the metal, forming copper atoms, a deficiency of positive charge would develop in the copper 2 nitrate solution. Notice we have a total of 4 positive charges and 6 negative charges on the ions depicted in this solution. Alternately, we could also take the viewpoint of negative charge. We could say that the solution around the zinc anode now has a deficiency of negative charge, and the solution around the copper cathode now has an excess of negative charge. The fact is that unbalanced charges cannot really exist in solutions. In every solution, the total positive charge of the cations must equal the total negative charge of the anions. So the process we described here could not really work with the cell right now. We'll drop a salt bridge into this cell between the 2 beakers. Some of the excess positive charge in the solution around the anode would be relieved by a gradual migration of cations away from the anode toward the cathode through the salt bridge. Similarly, some of the excess negative charge in the solution around the cathode would be relieved by a gradual migration of anions away from the cathode toward the anode through the salt bridge. So if we consider just the ions in the salt bridge, we can picture cations moving toward the cathode and anions moving toward the anode. And if we also consider the wires, we can picture electrons moving from the anode toward the cathode through the wires and the light bulb. So cations and electrons move toward the cathode, and anions move toward the anode. If we consider just zinc cations that came from the zinc electrode, they move into the salt bridge as they migrate toward the cathode, just like other cations. Now the copper cations that were already in the copper 2 nitrate solution around the cathode are cations too. So they will not enter the salt bridge, but will also move toward the cathode, where they will be reduced to neutral copper atoms. So we can summarize by saying that all cations move toward the cathode, and all anions move toward the anode, and electrons move from the anode toward the cathode through the wires. Here we'll summarize the main things you need to remember about electrochemical cells containing 2 metals and solutions containing their cations. Electrochemical cells are also known as voltaic cells. You may see this term in some textbooks. Oxidation always occurs at the anode. One way to remember this is oxidation and anode both start with vowels. For example, in the cell we've shown here, zinc metal atoms are oxidized to zinc ions. Reduction occurs at the cathode. Both reduction and cathode start with consonants. For example, in the cell we've shown here, copper 2+ cations are reduced to copper metal atoms at the cathode. If the anode is not made of an inert metal, it will lose mass as its atoms oxidize into ions. For example, this half reaction tells us that zinc metal oxidizes to zinc ions, thus dissolving into the solution. The cathode gains mass as cations are reduced to become metal atoms, which adhere to its surface. For example, in this cell, copper 2+ ions in solution are reduced to copper metal atoms, which stick to the surface of the copper electrode, thus increasing its mass. Electrons move from the anode to the cathode in the wires, from A to C. This makes sense because electrons are lost by the anode and gained by cations at the cathode. Cations move toward the cathode in the salt bridge. Both words start with cat, cations and cathode. This makes sense because cations are produced at the anode and used up at the cathode. Anions move toward the anode in the salt bridge. Both anions and anode start with an. It is important to remember that reactions in an electrochemical cell are always spontaneous. In another type of cell we'll look at later, an electrolytic cell, the reactions are non-spontaneous. In all electrochemical cells, chemical energy is transformed into electrical energy. It is good to study and be familiar with all these facts about electrochemical or voltaic cells.